Graph theory is one of those subjects whose origin we can trace back to a specific person at a specific time trying to answer a specific question. The person was a very famous mathematician. His name is Leonard Euler. The time was around the middle of the 18th century, and the place was a city in what at the time was Prussia called Königsberg. And what was going on was the city had, you can see in this map here, it was built around two rivers. They came together, kind of wrapped around this island and went out the other side. And it had all these bridges built across it. And evidently, the people of Königsberg were in the habit of walking across these bridges in the evening, just kind of taking in the scenery, very historic city. And the question they asked was, is it possible to plot a path where you cross every one of these bridges exactly once, so that you get the whole show, right? You see all there is to see without any duplication, and ending up back at the same place where you started, so that you can go on home or wherever else you were going that evening. So, it's about the mid 19th century. Leonard Euler I guess, became aware of this, and he started thinking about it. And his first approach to it was to say, look, there's a lot of information here that we don't need. I don't need to know how far apart the bridges are. I don't need to know how long the bridges are. I don't even know how wide they are. Any of that. All he needed to know was what connections existed, right? Which bridges connected which piece of land, and you can see how he simplified it in this diagram over here at the right. Hopefully that's familiar, right? That is the kind of graph that we were talking about in the previous lectures. You see, the edges here are the bridges. For example, these two edges would be these two bridges. These two edges down here would be these two. And the vertices are the land. So the island here would be vertex A. This kind of interior section would be vertex D. And then down here you've got the outer riverbanks. Those are B and C. So that was the first step Euler took in solving this problem. He reduced it down. He developed a model, if you will, that had only the components that he cared about, right? What things were connected to what other things and how. So before we can jump into Euler's really very elegant solution to the question, we are going to do a few more definitions, because we need to make this idea of a path around the city that has certain conditions, right? Every bridge exactly once starts where it ends where it starts. We need to make this a little more precise, right? And these definitions here are going to do that. So a walk between two vertices is exactly what you think it would be, right? Especially if you think of this as a map. This is the Königsberg map again. A walk just describes a path around these vertices. So for example, I'm outlining one here, right? We could start at V3, go up to V2, back to V3. Let's say we go back to V2. We can repeat. There's nothing wrong with that in the definition here. Then we could go over to V4. So the definition, it kind of explains how I would describe this, how I would write this mathematically. I'm going to do an alternating sequence of vertices and edges. So we started at V3, then took E6 to V2, then took E5 back to V3, then took E6 back to V2, then finally took E7 to V4. Hopefully you can see just from my example here why you can't just specify the vertices, right? Because sometimes there's more than one way, right? There's more than one way to get from V3 to V2. So we did have to include the edges to make it clear exactly which path we were taking. And again, if you match this up with the definition, it is an alternating sequence. We've got vertex, edge over and over again. and all of the vertices and edges I picked, are adjacent. So this is an example of what we would call a walk. Okay, now a trail is kind of a walk plus, right? So we start off by saying a trail is a walk that has an additional requirement, right? It doesn't contain a repeated edge. So my initial example here, right, of a walk, this is not a trail because where is it here? Edge 6 appears more than once. Right? So if I took that out, let's try another option here that is a trail. And I could go V3 E6, then let's see, V3 E6 to V2, E5 back down to V3. Then we could take E3 over to V4. Yeah, we ended up at the same place that way. All right, so if I were to just outline this here, it's V3 to E6, V2 back down to V3, and then we jumped over here to V4. So that would be a trail, right? It's a walk, consecutive alternating series of consecutive vertices and edges, but we never crossed the same edge twice, right? If you look at the edges here, 6, 5, and 3, there aren't any duplicates. Okay, a path, very similar, right? Very, very similar. In fact, it's practically identical to a trail. The only difference is, in this case, instead of being concerned about the edges, I'm concerned about the vertices, right? So here, we are never going to touch a vertex more than once. So again, if you look at both of my examples here, neither of these are paths, right? Because this one duplicates vertex 2, and this one down here duplicates vertex 3. Right? So none of those are paths. I don't know if we could really duplicate this particular arrangement because of that loop, right? Going from V2 to V3 and back again. Okay, a few more definitions, right? Three more, and then we'll wrap this one up. A closed walk is again, you see, we're constantly building on that one basic walk definition. A closed walk is a walk that has the additional requirement that it starts and ends at the same place. Right, so hopefully you're starting to see how the Königsberg problem is fitting into this, right? Because that was one of their requirements, that you had to end at the same place you started. Okay, so how could I do an example of this here? Well, let's say we have V1, take E1 to V2, and E2 back to V1. That's just a simple loop here around this little section of the city. It's alternating vertices and edges. Everybody is adjacent to the thing before it, and it starts and ends at the same place. And I would list the starting and ending point in here, right? So it is clear that happened. Okay, a circuit is a closed walk that contains at least one edge. Okay, no fair just picking a vertex and saying there's my walk. You have to actually go somewhere, all right, for it to count as a circuit. So a circuit is a closed walk that contains at least one edge and no repeated edges. Okay, so again, now you see, now we're really getting to what the Königsberg people were asking, right? It contains at least one edge, so you have to go somewhere. No repeated edges. Right, that was another one of the requirements. You don't go any place more than, you don't cross the same bridge more than once, and it has to be closed. Right, so it's a closed walk as well. So I mean, just to toss an example here, right? We could build on this one here. Well, actually, this one is also a circuit, right? This one meets both definitions. It's both a closed walk and a circuit. Or if I wanted to come up with a closed walk that wasn't a circuit, Do the loop twice, right? If I go V1, E1, V2, E2, then do it again. V1, E1, V2, E2. Now you're just going around it twice, right? That is a closed walk because it starts and stops at the same place, uh, but it does have that repetition, so that wouldn't be a circuit. A simple circuit is a circuit that also doesn't have any repeated vertices, except, of course, the first and the last. You have to repeat the first and the last, right? Because that's you're starting and stopping at the same point. So I know that's a lot of information, right? Really, you see 6 new definitions, and they're all kind of playing off of the same criteria, right? Some allow repeated edges, some don't. Some you have to start and stop at the same place, some you don't. So what I've done, right, is I've just taken all of that information and I've organized it here in this table. Uh, you might, if you're really kind of seriously studying this, you might ignore all of this stuff that I've got here in the beginning. Just do the row headings and the column headings, and try making your own table. Just as a way of studying, kind of helping to start get those definitions into your head. So that's the terminology that we need to be able to talk about this Königsberg bridge problem in a mathematically precise way. And that's what we're going to do in the next several lectures when we take a look at Euler's solution to their question.